Hello and welcome. So this is Dhirendra Tiwari. Today we are going to discuss a very important concept in electrostatics. That's about electric flux. So electric flux we define as the number of electric lines or electric lines of force that penetrates a given surface area. We already know that electric field E is defined as proportional to number of field lines per unit area, or the electric field magnitude is actually proportional to number of field lines per unit area. And we define electric flux as phi E is equal to E dot A. Flux is a composite quantity and it's a scalar physical quantity. Scalar means just like my wave, and it is a dot product of two physical quantities. First is electric field, second is area vector. Okay, let's try to understand these concepts step by step. What I mean by flux, for example, if we have electric field and our field line density is uniform, so this is a uniform electric field, and we have two different areas, so you can see the area first and the area second. Now you can see, depending upon the orientation of the area, our flux changes. All right, so if we rewrite this flux in details, the flux is equal to the magnitude of electric field times the area vector and cos of the angle between electric field and area vector, right? So what you can understand is basically flux is the product of the electric field times the projection of the area that is perpendicular to the direction. Don't worry, we will understand this idea very soon. So the first thing that we encounter in this formula of electric flux is not just the electric field but the area vector. The area vector, as shown here with the symbol S, if you write in vector form, this area is some area, okay, that is inside this disk, times the normal vector. Now the normal vector is shown by this arrow. So when you have a plane, let me take an example. Now this book represents an area vector, okay. Now every area vector has unique area times the direction of the normal. Now this concept is very important because we are going to use area vector throughout electromagnetism, and you can see we can define a unique area vector by taking some magnitude times the normal vector. So how do you actually do electric flux? We have a uniform electric field, and then there is a white area, okay. The area of this, you can see there is an angle between electric field and the area vector, and this angle is the theta. So if you have a simple surface which is flat or discrete, you make such a calculation where you use flux is equal to EA cos. So you can see here we have a continuous surface. You can imagine this is a patch on a football. Okay, football has several patches. Now this is a continuous area. Now in these kind of area where the area vector is continuously changing, right? If you take any patch, you can define the area vector and it makes an angle. If you take any other patch on this surface, it will have a unique angle. That is why here we have to use integration. So we define flux, the net flux is integral E cos theta times dA. All right. Let's understand things step by step and slowly. Okay, let's take a first example here. We are given a square surface of side L meter in the plane of the paper placed in a uniform electric field. So we are given a uniform electric field. Okay, this field exists in the plane of this paper. Okay, plane of this screen. And then we put a square surface, right? You can see a square. And now this square and the field has some kind of orientation by. So in this question they have asked what is the electric flux linked to the surface. The field lines are actually parallel to the surface, okay? They are in plane. So actually no field line penetrates this square. Normal vector of the square is out of the plane, is towards me, right? You can do a right hand curve rule. The area is in the plane, the direction of the thumb is towards me. The real angle between electric field and area vector is 90 degrees. Therefore, you can also say flux is equal to EA cos 90. Now this theta angle, which is given as the orientation, is just to trick you. The answer is 0. This question has been asked in NEET 2010. Now let's move on to the next question. So we are given a cylinder of height 2L and it has a radius F. It's placed in a uniform electric field. Okay, our first examples are about uniform electric field. The reason is we want to go step by step. Okay, what is the flux entering this non-conducting cylinder? Now non-conducting, because if it is conducting then no field lines would penetrate and inside the flux will be 0, so no flux will happen. Key and important thing in calculation of electric flux is we only have to worry about area perpendicular. This is the area that is perpendicular to this electric field. So the another way of expressing flux is phi is equal to basically electric field times the area that is perpendicular, right? Because the area perpendicular in this case you can see is very simple. Just give it a thought, give it a try. You will see it is simply a square patch, right? So the area perpendicular is 4L square, right? So our flux is going to be, all right, so the answer is, now this is a logical question. It gives you clear understanding of what is flux, okay? Now I want to go to one more example because you know flux is hard to imagine. What is easy to imagine is rain. So always think electric field is like rain, okay? So some rain is falling towards the ground, all right? And now you can always imagine area vector is like umbrella. Suppose you hold this umbrella in this manner, here is the handle of the umbrella, then you can clearly see there is a 0 degree angle between the handle of the umbrella. The handle of the umbrella, I will say, is the normal vector of the area. And this is the area vector A. And this is the electric field E. So you can imagine in everyday life when you have a rainy day, what you try to do is you try to rain flux by orienting your umbrella 0 degree with respect to the rain, right? Because this is in line with the rain direction, then you will have the maximum flux. Now if you tilt this umbrella, suppose we tilted this umbrella at an angle, say theta, all right? Now in this situation, these raindrops, okay, they are going to go through. These raindrops, they are going to go through. So you can see our flux, which was maximum, our maximum flux was E times A, because the angle was cos 0 degree, right? Now, if you have any other orientation, then you will have EA cos theta, right? So always imagine electric field as the rain direction and area vector as an umbrella, where the area of the umbrella is a scalar quantity and the handle of the umbrella is the normal vector. Then you could easily visualize these things. Okay, so let's move on to the next problem. So now I'm given a hemispherical bowl. Now you can see this bowl is exactly in the shape of an umbrella. Now the electric field is uniform, right? And you can see here, for flux calculation, what do we need? We need the area that is perpendicular. All right. So you can see the area that is perpendicular to the direction of electric field. We can clearly write it as a circle. Although this has a complicated shape, right? It has a complicated shape, but effectively it is protecting in this area, which is a disk. Now this disk, which is a circle, has a size pi times r square, right? So we can easily calculate the flux will be E times pi r square. Now let's see this one. Now this is the same concept, and here I really want you to understand what is the flux. Now flux through this kind of hemispherical bowl, we can clearly see is the product of the electric field times the area that is perpendicular to the uniform electric field. Now you can see that will be this semicircle, right? Now you can clearly write down what will be its value. So you can see this is a half of the circle. So that is half pi r square, right? So we can write the flux is E times pi r square by 2. The answer will be C. I think this is going to be our last conceptual problem. Now these problems were specifically based on uniform electric field, and we placed some objects of different shapes. Now here you have a cone. Now in this question what is asked is, what is the flux entering through this non-conducting cone? Now again, just imagine electric field is like rain, and you have this cone in its path, right? So you can clearly see for this particular case, right, you have this triangular region. Now the triangular region represents the area that is perpendicular to the direction of electric field. Now let's try to imagine and visualize this. So we have a uniform electric field and we have this area. This area is simply half of the base. Now what is the base? Base is 2r, and the length is also half. Flux will be E times r square. The answer is A. Thanks a lot for your attention. I will bring more problems based on vector form of electric field and area vector in the next lecture, and then we are going to do advanced problems based on calculus for complicated geometries. Thanks a lot for your attention. If you like this lecture, please subscribe to our channel. Have a nice day. Bye.